Swayam Prabha. Digital India. Educated India.
Today let us look at a few classes. The strong perfect graph theorem, if you remember, stated that a graph is perfect if and only if there is no hole or anti-hole in it. So I'll write it here. No hole or no hole or anti-hole. What is hole? So in your graph, suppose you identify a cycle. So hole means, I should say odd hole and odd anti-hole. Odd hole or anti-hole. So suppose you identify a, say, 5 cycle. 5, 7, 9. 3 does not matter. 3 we don't consider as a hole. 4, 6, etc. are okay because they are even. Odd hole means if you get a cycle which is of odd length greater than or equal to 5, and then so there can be many things here, no? So it is in a graph, but then if you concentrate on these vertices alone and see what is the induced subgraph on that set of vertices, that should be just that cycle. There should not be any other things like this. This is a chord, right? And no chord should be there. So nothing like this. Induced subgraph on that should be just such a cycle. So if you simply say a cycle, that only means that we have those edges which is forming the cycle. Other edges also may be there on that, right? When you insist that the induced subgraph on the set of vertices forming that cycle should be just that cycle, that means there is no more edges in that, no other edges, right? That is what is called a hole. When we say odd hole, we mean that the number of vertices on that hole is odd, with 5 or 7 or 9. Not 3 is not considered hole. So anti-hole is just the complement of that hole. So for instance, if I take this hole, what would be an anti-hole corresponding to that? This should be the anti-hole. Because it is a 5 cycle, then the anti-hole is also the 5 cycle here. So but if you had taken a bigger graph like this, suppose, this is 7 vertices, right? So now you can create, so it will be like this. All the edges which are not red, right? This graph. So it's quite easy to construct an anti-hole because you just take a set of vertices, just remove a cycle from that. The remaining, whatever is remaining, is the anti-hole. Yes. So now that we know that it's proved in the 2000, I told as 2002 or 3, Paul Seymour and his team proved that this statement is correct. A perfect graph is exactly those graphs which does not contain odd hole or an odd anti-hole. So now look at graphs which are kind of giving some natural restriction on the length of induced cycles in it. So the first such example is Chardal graph. So a graph is chordal if and only if it does not contain any induced cycle of length 4. What does it mean? You take any cycle in a chordal graph. If it is of length 4 or more, then what can you expect in that? It's just not induced. That means there are some chords. For instance, if you locate in the chordal graph, suppose you see this cycle, then there should be some chord in it somewhere, right? Then you see a smaller cycle here, right? Like this. There will be some other chord. So now you see a smaller cycle here, but then that's a triangle. That's okay. If you go to this cycle, then what will happen? Here you see a 4 cycle, then you need a chord, maybe this one, right? So now both are triangles. Now it's okay. Yeah, all cycles have to be either they should have a chord or they should be a triangle. This kind of graphs are called chordal graphs. These chordal graphs were studied much before because of its applications. I guess some electrical networks people. I think it was called rigid circuit graphs at some point of time. I don't know what it means. And there were several applications in which chordal graphs appeared, right? So, say there are many natural situations chordal graphs will appear also. For instance, if you, you can think of many such situations. For instance, a visibility graph or something like that, right? It's naturally some 4 cycles can be avoided. And let's see some properties of chordal graphs. So one property about chordal graphs which is interesting is about its minimal separators. I hope all of you know what is a separator of the graph, right? So the separator means, so it's some set. Suppose this is a graph. So something like this. So if you remove this set, you get 2 parts, right? Separator, minimum separator. The cardinality of the minimum separator is what? It's the vertex connectivity, right? The minimum number of vertices to be removed. So, but minimum separator means so you find out some set of vertices, and then if you remove it, then the graph should separate, and that should be minimum cardinality. There is also something called minimal separators. What can be the difference between minimum and minimal? Anybody else? Can anyone suggest a reason to use minimal instead of minimum? Okay, have you seen this word being minimal used instead of minimum sometimes? So we refer to here, at least what we mean is, if you take any subset of it, there is no separator in it. So if you take a separator, and I will tell that it's a minimal separator if no proper subset of that set of that vertex set will form a separator. That means if you want to disconnect the graph, you have to remove all of these things. You cannot remove a part of it and get it separated. There will be still connections with 2 parts. When I say minimum means it is by number, right? It should be the smallest, right? Minimal need not be minimum. Sometimes it's just that no proper subset of it cannot be a separator, but there can be somewhere else some separator which is smaller than this, right? It's quite possible that I get some other piece here. Yeah, something like this. See, if I have to remove this entire set to disconnect the graph here, but then the minimum is somewhere here, right? So because this has nothing to do with that, right? So now, what is an interesting property of a minimal separator? And so a property of the minimal separator is like this. Suppose this is separator. So suppose these are vertices of the minimal separator. Now, can you see that each vertex of a minimal separator should have at least one edge going to both, at least one edge, both sides. Can anyone see tell me a reason why it should be like this? So for instance, if I take a vertex, it's not possible that I have this along, or maybe a lot of it. Yeah, there can be a lot of edges to this side, but suppose no edge to this side. Why this is not possible? Yeah, because in that case, this part alone is enough to, this part alone, see this portion alone is enough to disconnect it, because this vertex is not really connecting to that side, right? So therefore that is not a minimal separator. A subset of this set is able to disconnect the graph, right? So therefore to both sides it should have edges. Every vertex, each vertex of it should have edges. Let us look at a chordal graph and think about the minimal separator of a chordal graph. What is interesting about the minimal separator of a chordal graph? So the statement is that the minimal separator of a chordal graph has to be a complete graph, induced subgraph. If you take a minimal separator and look at the induced subgraph on it, it should be a clique. It should be a complete subgraph. Why is it so? Can anybody see the reason for that? Suppose, let me just see this. Suppose this is a chordal graph and I just draw a minimal separator. Suppose this is a minimal separator of the chordal graph. So the claim is that there should be all edges here. Why? What is wrong if at least one edge is missing? Suppose there is two vertices here where this edge is missing. What's wrong? Any idea? I can tell you, I can remind you what property we knew about the minimal separator of the chordal graph. Minimal separator of any graph. So this vertex should have one edge here, one edge here. More edges can be there. One edge here from here, one edge here. More can be there, but at least one, right? Does this picture tell you why this dot between these two vertices and edge should be there? It's not possible to for that edge to be absent. That's what you're saying. What happens? Yes, we can try to form a cycle. For instance, wherever this is reaching and wherever this is reaching, we can get the shortest path here. Similarly, here also we can get a shortest path. In fact, starting from here, among all the neighbors, or if there are more neighbors here, we can take from this set to this set the shortest path, right? And then what happens is something like this will come, right? Maybe I'm trying. Yeah, finally something like this will come. I don't know which exactly will be the neighbor which starts coming to here. And what is good about it? Let me, something like this will be seen. So what is good about this thing? What is contradicting here? Yeah, there should be a chord, because it's a 4 cycle now you're seeing. There should be a chord. Where there are many possibilities for a chord, right? But where can the chord be? See, one possibility for the chord is that it can be somewhere here, maybe. But that's not possible because we are taking the shortest path there, right? In this portion, no chord. This portion, there is no chord. This portion, there is no chord. And this vertex also cannot send anything to here, because we are taking, among the neighbors, we are taking the shortest connection, right? So the chord can be either across, that means from here to here, but that's not possible, because any edge going from here can only go to the separator, because it cannot jump over the separator, right? So the chord can only be here, right? So that means this edge cannot be missing. That is why this entire separator should, like, there won't be any absent edge inside that. So this should be a clique. This is one interesting property of chordal graph. Now we have used the defining property of chordal graphs to reach this conclusion, right? That means any cycle of length 4 or more should have a chord. That was the defining property of chordal graph, no? And so therefore you cannot expect the same property on other graphs, right? It's a very special thing about the chordal graphs. So this is a useful property. So minimal separators are cliques. Why is it useful? So let's say. So from this thing, using this thing, we can get a very interesting, very useful property of chordal graphs. Namely, any chordal graphs contains a simplicial vertex. What is a simplicial vertex? A simplicial vertex means if you look at that vertex and its neighborhood, that should induce, that neighborhood along with that vertex should induce a complete graph. Something like this. For instance, if I take this vertex, so it should have all the edges here, right? It should be a clique. I'm not saying that all vertices will be like this. If all vertices are like this, then what will happen? If all vertices of the graph are simplicial, then what can you tell about the graph? It should be a clique, because that's not possible for other graphs, right? So we are only claiming that there is one simplicial vertex. Then you will one simplicial vertex. There will be one vertex such that it's that vertex and its neighborhood would induce a clique. That's good, but you will wonder what is good about it, right? So it's some curious property. That's it. But what is good about it is, if you find a simplicial vertex, then you can think of removing that simplicial vertex, right? Then what is left is again a chordal graph. Why is it again a chordal graph? Because what is left is an induced subgraph, because if you remove one vertex, then it's again an induced subgraph. And if the original graph satisfies the condition for the chordal graph, that means there is no chordless cycle of length 4 or more, then the induced subgraph also cannot have, right? Because if the induced subgraph had a chordless cycle of length 4 or more, that was there in the original also, no? So presence of one new vertex cannot destroy this chordless cycle, right? So therefore induced subgraph are also chordal. If a graph is chordal, every induced subgraph is also chordal, right? So what is good about it? I remove one simplicial vertex. The remaining graph is again a chordal graph. There should be another simplicial vertex in it, because that's what we proved, no? And you can remove that vertex. There will be another simplicial vertex in it. Is it true that those simplicial vertices are already there before you removed the vertex? The earlier vertices? No. Those might have appeared because you removed the earlier vertices. It's possible that you have this simplicial vertex now, but then the earlier vertex you removed was something like this, right? And earlier vertices you removed was something like this. This probably together, its entire neighborhood was probably not simplicial. This edge was missing. But then when you remove these two, then this became simplicial. That's all. So that is very nice. In fact, one after the other, as you remove vertices, a sequence of simplicial vertices will come. That means the vertex set of the chordal graph can be arranged in an order, like first a simplicial vertex, then a simplicial vertex in the remaining graph, then a simplicial vertex in the remaining graph, like that, right? And if you read this ordering, this is an elimination ordering. This is called a perfect elimination ordering. It's called usually we write it as PEO, perfect elimination ordering. I'll tell you why this where this word comes to. You will wonder why this elimination ordering. But before that, let's get to the simplicial vertex. So I only motivated why a simplicial, the search for a simplicial vertex is interesting, right? So now, how do I show that there is a simplicial vertex? My claim is that that property of all minimal separator being inducing cliques, that will help us to show that there is a simplicial vertex, right? So how do we do this thing? We can do an induction, because at least we have guessed the thing. If you ask me how do I guess, okay, anyway, somebody by observation or something you guess. No, any simplicial vertex you remove. No, any simplicial vertex can be removed. It does not matter, because you first pick up a simplicial vertex which is guaranteed to exist and remove that vertex, that is eliminated first, and then in the remaining graph there is a simplicial vertex with respect to the remaining graph. Other vertex, simplicial vertex, not necessarily, no. For instance, it can be something like this. So suppose this is a clique, and then I have many vertices like this. So you see, these are all simplicial vertices here, see. So I can remove any of them, right? But then this is not connecting to everything. See, this is right. So this first, in any order you can remove, does not matter. They are all simplicial vertices. But then once you remove all of them, and then any of these things can be removed, right? But on the other hand, before this is removed, this vertex is removed, this particular vertex, see, is not a simplicial vertex, because this is connected to this also, it's connected to this also, this edge is missing, right? So you have to, certain ordering is there, but at some point of time there will be many candidates. There can be many candidates, right? Any candidate is fine. You can pick up your favorite. That's why you can one question may be to count how many perfect elimination orderings are possible, right? There are such questions also, enumeration questions. So I hope you understood what is this perfect elimination ordering and what is a simplicial vertex. Now my interest is to prove that there exists a simplicial vertex in a caudal graph. And the only tool I am going to use to prove is the lemma we proved just before, namely all minimal separators of caudal graphs are inducing cliques. They induce cliques. And remember, to prove that lemma, we only use the defining property of caudal graphs, namely any cycle of length 4 or more should have a chord. Now how do we do this thing? We can use induction, because now that I have told you the theorem, right? Then we can try to use induction. Otherwise, without knowing the theorem, you cannot use induction. But if somebody tells you the theorem, and then you can try to use induction. That's a proof technique, right? So just if you can guess a theorem by working out with examples, or sometimes you get an intuition that this thing may be correct, then one natural thing to try is induction, right? But now you see, you have done many inductions in your mathematics. Students might have done many proofs using induction. But induction, sometimes it works very easily, sometimes it is somewhat tricky, right? For instance, it may not work. So this is some such situation. For instance, so you can start with smaller graphs, it's correct. So now see, suppose you proved for all graphs with all caudal graphs with n-1 vertices or less, that there exists a simplicial vertex in it. Now you get an n vertex caudal graph. Suppose this is an n vertex caudal graph. Now you want to show that there is a simplicial vertex in it. How will you go about it? How does the induction hypothesis help? You want to show that there exists some vertex somewhere here in this thing, so that if you look at the neighborhood of it, along with it should form a clique. So what may be so it is that we know that there are some, once you remove any vertex, you know that some simplicial vertex is existing, right? So some simplicial vertex will come, because n-1, but does it mean that in this graph, bigger graph, there is a simplicial vertex. Maybe because you removed one vertex, the simplicial vertex came. Because you try removing this vertex, suppose, and maybe this is a simplicial vertex which is occurring now, but then it's possible that there was an edge here, right? And then this simplicial vertex is not a simplicial vertex of the bigger graph. You understand what I'm telling? See, this edge may be there. I'm trying to remove this vertex, make it an n-1 vertex graph. And the question is, can I make use of the simplicial vertex of the n-1 graph, the graph on n-1 vertices, as the simplicial vertex of the bigger graph? Not necessarily, right? Because this may be the simplicial vertex here, but then unfortunately the vertex you removed may have an edge to that. Yeah, there can be some situations where it's not so easy, right? Yeah, I guess maybe if you try really hard, probably you may be able to, you should try to prove it like this. But so there is something slightly stronger we can prove. There is one simplicial vertex. We will prove that there are two simplicial vertices. That two non-adjacent simplicial vertices. Not just one, two of them, and two of them such that they are not adjacent to each other. But you will tell me that complete graphs are caudal graphs, right? Complete graphs does not have even non-adjacent vertices. They are all simplicial vertices, but they are non-adjacent at all. So then how can you have two non-adjacent vertices? So we should avoid that case unless it's a complete graph. Unless it's a complete graph. I think this is what we should set up.